Hello. Today we are going to talk about binary trees. So your first question is probably, what is a binary tree? Well, simply, it's a tree. If you know what a tree is already, good. If you don't, then you'll have to look up one of the other videos that we've created. A binary tree is a tree with each node having at most 2 children. Hence the term binary. Okay, so here is a simple algorithm that you can use to create a binary tree. This is written in Java, but you could use it in other languages as well. And as you can see, there is a variable to store the value you would have on the left side, if anything would be stored there, and the value you would have stored on the right side. The nice thing about binary trees is that you know that each node can have at most 2 children. Therefore, you can have a variable for each one, and you don't have to second guess yourself on how many possible children each node can have. Okay, when you are making a tree, there are different ways of traversing the tree. That is, to search the tree or to output the tree, or to find each element in the tree. The first one we're going to talk about is pre-order traversal. What this means is that you would start at the node. You would go down the tree as normally, and the node that you start at was processed first or outputted first. And then after that, the children are processed recursively, starting from the left and then to the right. Here I show an algorithm that does this recursively. And if we were to look at this visually, well, here I have a tree as an example, and you could see I would start with the top node. That's where you always start. And for pre-order traversal, you would output that right away. So you would write A, then you would go to the left child, which would be then B, and then you still go down to C, and there's no more children after C, so you'd go back up and go to the right child, which is D, and again, no more children there, so you'd go back up to the right child of A, which would output E, then F, then G. Post-order traversal. This means that each node is processed after the children are processed recursively. So it's almost the opposite of what we showed you. And here's an algorithm for it. If we were to look at this visually, here I have a tree again, and it would output, you would look at G first, but you would not output G, you want to output the left child, so you would go to C. But then you would go before you output C, you have to output the left child of C, which is A. A has no children, so you would output A. Okay, now you have to output the right child of C, which is B. And that's all the children C has, so now you would output C. Then now you would go back to G, but you have to output the right children of G, which would be D, and then E, then F, and then you would output G. Okay, the third and last traversal is in-order traversal. This means you would basically read the tree in order, assuming that the tree is in order to begin with. So you would read the left child, and then the current node, and then the right child. If your tree is sorted in order, then this will output the list in the desired order that the tree already has. So here's the algorithm for it. That is, again, done recursively. And here is an example. So I would output A, and then B, then C, then D, G, and then E, and then F. You see I changed the letters here to confuse you a little bit. Okay. Now, one way to use a binary tree is to use it to store arithmetic expressions. You can make simple expressions using the tree. To do this, the value of a node would be obtained by applying the corresponding operator to the children. the leaves are always the numbers that would be stored in the tree, and the rest would be the other nodes would store the different operands that are applied to the numbers. So here's an example. You see I have a binary tree, and you see I have A, B, X, and Y are stored at the leaves at the end. We'll assume those are variables that store numbers. Above that we have different operand symbols, 2 pluses and a minus. And you can see here by the equation here that tells us what this means. The A plus B would be together calculated. And then it would be that minus what's on the right side. It looks pretty straightforward. Now, we talked about the different traversals you can do: pre-order, post-order, and in-order. Note that you can use these different ways to traverse the tree to rewrite the equations of the tree. So if you did it by pre-order, you would go the minus sign, and then the plus sign, and then the A, then the B, then the plus sign, and X and Y. Likewise, if you did it in post-order, it would be A, then B, then plus, then X, then Y, then plus, and then minus. And if you did it in order, it would be identical to what you just saw before, except the brackets wouldn't be there. You would have to insert the brackets yourself. You can insert brackets around each left and right node of what you're calculating. Okay, now we are going to talk about binary search trees. Well, that's a binary tree where the elements or numbers stored in each node are arranged in order. In this case, if they are numbers, they can be in numerical order, or if they're letters or words, they can be in alphabetical order, and so on. Each element then is compared to each other by using the element stored in the node. And here's an example. If we were to put this tree here that you have in order, then in order you would get 1, then 5, then 6, then 10, 15, and 17. So you can see that this list is in order if we used in order traversal. Now how would you insert that? Well, we'll talk about that in a minute. Implementation. How would you implement a binary search tree? Well, it's the same as a binary tree. You would have a reference to the left subtree, the right subtree, and it would be easier if you had a reference to the parent node for each node. But also you need a fourth element called the key. And that's going to be a variable that stores the value of the number that you're currently looking at. Now, if you're searching a binary search tree, how would you go about searching it? Say if you're looking for a certain number, how would you search and find that number in the tree? Well, it's pretty simple. So you would compare the number you're looking for to the first node at the top of the tree. If it's less than the element of the current node, you would go to the left subtree. If it's greater than the element of the current node, then you would go to the right subtree. And then you continue this process until you either find the tree or you reach a point where there are no more nodes to follow down, in which case it does not exist in the tree. And here's some code for it, pseudocode. Here's a property for you. If you're looking for the maximum and minimum value of the tree, obviously the maximum tree node would be stored in the rightmost node, and the minimum would be in the leftmost node. Now, if you're looking for the successor of a key, or the successor to a node, what does that mean? Successor means that it would be the node with the smallest key that is still greater than the current key you're looking at. Here's some pseudocode for it. Okay, for example, if we were looking at this tree here that we have in front of us, and we're looking at the node 5, well, we could say that 10 is the maximum key if you're looking at the subtree that starts at 5, and 8 would be the successor to 5. Now we're going to talk about the predecessor of the key. This is almost the opposite of the successor. Instead of looking for the next one, you would look for the previous one to the node that you're currently looking at. So here, if we're looking at the node 19, and you're looking at the tree to it, 14 would be the predecessor, and 10 would be the minimum key in that tree. Okay, now we're going to consider how would you insert something to the binary search tree. Well, if the element that you are currently trying to insert is less than the element in the current node, it has to be inserted somewhere in the left subtree. If the element is greater than the element in the current node, it has to be inserted in the right subtree. And you repeat steps 1 and 2 until you eventually find a node with an empty subtree, in which case you insert the node there. And here's some pseudocode for it. And here's an example. Suppose we are inserting 14 for the first time. You would compare 14 to 10. Well, 14 is greater than 10, so you go to the right tree. You would compare it to 15. Well, it's less than 15, so you would go to the left of 15. There was nothing at first that was stored to the left of 15, so that's where you insert 14. Now, deletion in a binary search tree. Deletion is a simple idea. You search for the item that you wish to be deleted the same way that we previously talked about, and then you would delete it from the tree. But we have one problem here. Suppose that the item that you were trying to delete has a child, or what if it has 2 children connected to it? Well, if you delete that node right away, then everything else that was connected to it would also be deleted. So you have to consider that. How? Well, if you have one child, then that child would take the place of the parent that is to be deleted, and that's all you have to do. If you have 2 children attached to the node, then, well, visually you would see that you would take the successor or the predecessor and use that to replace the current node that you were deleting. Okay, here's some pseudocode for it. Now, notice here, in this part where you are finding the successor, and instead of deleting the node that we are trying to delete, we actually replace the value stored at that node with the successor's value, and then we delete the successor. This causes less confusion. We don't have to rearrange the nodes entirely. This way it's a bit easier. Okay, moving on. If we have an example, if we were to delete 5 from this simple tree that I made, well, if you look at 5 does not have any children attached to it, so you would just delete 5 and you're done. In this tree, if you want to delete 6, well, 6 has one node attached to it, that's 7. And so you would replace 6 with 7, and then you would be done. Okay, suppose you want to delete 5 from this tree. 5 has 2 children, or 2 branches from it. So what do you do? Well, you would take the successor, or the predecessor, whichever one is up to you. In this case, I'm taking the successor, which is 6, and I'm replacing 5 with 6. And notice that everything that was attached to 6 originally falls in place. There is a problem here. Suppose you had 6 only has a right node, 7, but what if it had a left node? If it did have a left node, then notice that well, you can't have 4 as a left node, then you would be missing something. So the left node would have to be rearranged accordingly. you would probably make the left node attach somewhere to the left of 6. So you would rearrange that with 4. Okay, that's everything I have to talk about for binary trees. I hope you learned something today, and we'll see you next time.